Hello, and welcome to the Chapter 16.7 lecture on change of variables in multiple integrals. So what we're going to learn is the multivariable analog of u substitution. So recall from back in Calc 2, you did u substitution by doing something like, in this case, x is the tangent of u, which you would have done because 1 plus tangent squared is secant squared, and then you would have that dx is secant squared u du. And then you would substitute that in to transform the integral into something like this. So critically, we let x be some function of u, and then we did a substitution. And that substitution wasn't just replacing x with that. We also had to change the dx part to some stretching factor involving u, as we'll come to think of it. Now, in multiple variables, the reason that we'll want to do this will be to transform the region of integration to some other region that might be easier to deal with. So we'll be letting x be g of uv and y be h of uv, where u comma v are the variables that we want to change to. And we actually already did something like this. Polar coordinates were transforming from one coordinate system to another, and it transformed shapes like circles into nice rectangles that were easier to integrate over, and that was the whole point of polar integrals. So in polar integrals, we let x be r cosine theta and y be r sine theta, and that's exactly an example of what we're talking about. Now, change of variables can change the areas of corresponding rectangles in the Riemann sum, stretching and shearing them. By that, we mean that we might have our nice typical xy Cartesian coordinates originally, but when we do our transformation to the UV coordinate system, then our squares or rectangles that are the bases of the Riemann sums might get sheared out, made bigger or smaller in area, and that will affect the end result when we integrate over it. And we'll therefore need to compensate by multiplying the integrand by the stretching factor of the transformation t in order to cancel out this local planar stretching of our transformation. And this thing that we'll need to multiply by to cancel out the stretching out is the two-dimensional analog of how in ordinary u substitution we would multiply by, in this case, secant squared of u, in order to cancel out the stretching factor when we move from x to u under this coordinate transformation. Except now we have an actual picture to understand geometrically why we have that. And that local stretching factor that we must multiply by to cancel out the local stretching of our change of variables is called the Jacobian, and it is defined as this. J of uv is this determinant. Both of these are just different notations. I'll be avoiding this notation. I'll just be using J of uv, and so does the textbook. And why is it this determinant? So recall that the determinant of a 2x2 matrix is the area of the parallelogram that the vectors in the matrix form. We touched on this briefly. Given a 2x2 matrix ABCD, then if we consider the vector CD and consider the vector AB, they form this parallelogram, and the determinant AD minus BC is the signed area of this parallelogram, in the sense that if we move counterclockwise in accordance with the right-hand rule, the determinant will just be the area, while if we move counterclockwise, then the determinant will be the negative area. So for example, if we consider the two vectors 1, 2, and 2, 1, and consider the area of the parallelogram that they form, that will be the determinant of 1, 2, and 2, 1, which is 1 times 1 minus 2 times 2 is minus 3, which means it has area 3, and the reason for the minus sign is that if we have 1, 2 first, then we're moving counterclockwise, and that makes it negative. Okay, so why are we covering this? And why does it appear in the formula for the stretching factor? Well, the stretching factor shears out the little squares around a point that form the bases of the rectangles or rectangular solids in the Riemann sum, and it shears them out into parallelograms. And we'll need to multiply by the area of that parallelogram that it is locally sheared out into, because that area over the area of the initial square, which is 1, is the stretching factor. So we have this, since the directions that the little unit squares are sheared out into have to do with the partial derivatives. So the area of this parallelogram is this determinant. So let's do an example. Let's compute the double integral of xy over the region R defined by x squared plus y squared less than or equal to 4 in the first quadrant. So our region R looks like this. It's a piece of a disk in the first quadrant, and this change of variables will convert this disk on the xy plane to a rectangle on the r theta plane. Step 1 with all of these problems is to find a new bound. We can do that by substituting. Our original bound was x squared plus y squared was less than or equal to 4. We do our substitution, and we have this. And that's the same as r squared times cosine squared theta plus sine squared theta is less than or equal to 4. And of course, this is 1. So we just have that r squared is less than or equal to 4, i.e. r is less than or equal to 2. And the fact that we're in the first quadrant, that means that theta is between 0 and pi over 2. So we have our new bounds, that r is between 0 and 2, and theta is between 0 and pi over 2. And these are nice rectangular bounds. So it looks very much like this picture, except that's a 2 now, as this was a 2 before. Okay, now that we have our new bounds, we want to find the Jacobian. And then our double integral over this original region will be the double integral over our new nice rectangle with our new bounds of xy after we do our substitution times the absolute value of that Jacobian. So what is that Jacobian? Here's our formula. And here, instead of j of uv, we're just doing j of r theta, just using different variable names. Okay, so just writing different variables. Instead of uv, we have r theta. So we want the Jacobian, j of r theta is del x del r, del y del r, del x del theta instead of v, etc., where x is r cosine theta and y is r sine theta. Okay, so del x del r, that's the partial derivative of r cosine theta with respect to r. That is cosine theta. Similarly, del y del r is sine theta. Del x del theta is negative r sine theta, and del y del theta is r cosine theta. And we compute that determinant, AD minus BC, is r times cosine squared theta minus negative r times sine squared theta. So we have r times cosine squared plus sine squared, and as always, this is just 1. So we have r. And we're interested in the absolute value of that Jacobian. But the absolute value of r is just r in the bounds that we found of r being between 0 and 2. So we don't need to worry about that. Okay, so that r compensates for the stretching that we're doing, going from one coordinate system to the other. Okay, so we found that our new bounds are that r is between 0 and 2, theta between 0 and pi over 2, and we found that the magnitude of our Jacobian is r. So now we plug that in, and we have successfully transformed this integral into one with different variables. And that transformed integral looks like this. Originally, we were in the xy coordinate system. What we do is we replace x with its value in the r theta coordinate system. X is r cosine theta. Similarly, y is r sine theta. We need everything in terms of r and theta now. And then we multiply by that Jacobian in magnitude, which we found to be the r. And that is our transformed integral. And now it has nice rectangular bounds, and one can compute that, and one ends up getting 2. I've skipped steps there. At this point, we know how to compute double integrals with constant bounds. So the point there was the setup. And what I want to point out is, look at that. Isn't that just what we did for polar integrals? It's exactly what we did for polar integrals. We just converted to our new bounds within the r theta coordinate system, and we didn't forget to stick that r there. And now we understand that that r is precisely the Jacobian to compensate for the stretching factor. There's a different light on that r. However, this method is much more general than just applying to the polar system. Otherwise, we wouldn't be learning it because we already have the polar system. And here's an example of a very ugly looking region, but which can be nicely transformed into a rectangle under an appropriate coordinate substitution. Okay, so look here, we have these bounds of x minus y squared is -4, and x minus y squared is 0. All I've done is taken these and rearranged them slightly. It'll help make a point clear. And we also have the bounds of x is 9 minus y squared and x is 16 minus y squared. I'll write these as x plus y squared is 9 and x plus y squared is 16. Now, look what's happening here. So here that means that x plus y squared varies from 9 to 16. And here this means that x minus y squared varies from -4 to 0. And those are nice constant bounds on these expressions respectively. So let's call x minus y squared u. We'll just give it a new variable name. And we'll call x plus y squared v. And now what happens is that u has constant bounds of -4 to 0, and v has constant bounds of 9 to 16 under this coordinate transformation. So on the uv plane, that means that this region R, which had been bound by those, becomes bounds of v going from 9 to 16, as we found here, since this guy is v, and u going from -4 to 0, since that guy is u. In a nice rectangle, well, that is way nicer to integrate over. So this is screaming for a coordinate transformation from here to here. And at this point, we need to find that Jacobian and then plug it in, and we'll have these nice constant bounds. In any one of these types of problems, step 1 is always to identify the new bounds, but we just did that. We're done. The new bounds are u going from -4 to 0 and v going from 9 to 16. Okay, so now step 2, we compute the Jacobian. The Jacobian is this formula, that determinant, and then we'll take its absolute value, plug it in here, and then we can compute it with our nice rectangular bounds. Now here's an important note. To compute that Jacobian, in the Jacobian we'll have expressions like del x, del u, del x, del v, etc. So what we'll need is x and y in terms of u and v. So our having u as x minus y squared and v as x plus y squared is not sufficient. We need to solve for x and y in terms of u and v, so that then we can take del x, del u by taking the partial derivative of whatever x is in terms of u and v. So in this infographic, they just tell it to you, but in practice, we would need to derive that. A nice way to derive that might be just elimination. Adding these two together, we eliminate y, and we have that u plus v is 2x. So x is u plus v over 2. And similarly, if we subtract these two, we eliminate x, and then u minus v is -2y squared. So then y is the square root of v minus u over 2. Okay, so these are the expressions of which we take the partial derivatives in computing the Jacobian. Let's do that. Okay, so the Jacobian is this. And again, those x's and y's, we're going to be using this for x and y in terms of u and v. Del x, del u, v is constant there, so u over 2 becomes 1/2. Similarly, del x, del v is also 1/2. Del y, del u is by the chain rule, -√2/4 root v minus u. Remember that whenever you have a square root and taking the derivative, square root of x is x to the 1/2, and then taking the derivative, you just pull down that 1/2 and decrease that by 1. So it's the same thing here. I pull down this 1/2, and then to the power of -1/2, that means divided by the square root, and then chain rule, pull out the minus sign and the square root of 2, and we have that. And likewise with del y del b. Now we can compute that determinant. AD minus BC is root 2 over 4 root v minus u. And if we want, we can rearrange that as 1 over 2 root 2 root v minus u, or 1 over 2 root 2 times v minus u. So these are all just algebraic rearrangements. Okay, so we found our new bounds, and we found our Jacobian. So now we can rearrange our desired integral. So the integral over that original region of y squared dA is the integral from -4 to 0. This will be our du. And from 9 to 16, that will be our dB. Okay, and we want to replace everything to be in terms of u's and v's. So remember that we had a y squared there initially, but y is that in terms of v and u. So y squared is the square root of v minus u over 2 squared. So our y squared is v minus u over 2. Okay, we take that and multiply by the magnitude of the Jacobian, and we computed that that is 1 over 2 root 2 times v minus u. Okay, so we got our initial function in terms of u's and v's. We multiplied by our Jacobian on the inside. We have our new bounds in terms of u's and v's, and that is du dv, making sure our variables line up with the bounds. And that is it. We have transformed our integral to be over this new coordinate system, and now it has nice rectangular bounds. And now it's a matter of computation. This can be simplified a bit. It isn't too bad. It's certainly much nicer than having to break this up into 3 regions and the unpleasantness of this initial very non-rectangular region. And to finish computing this, I'll put up this slide. So we got that it is this integral. That's exactly what we found. And you can pause the video if you want to go through the computation of this, although it is essentially doing calculus 2 twice. Let's do another example. The purpose of this example is to illustrate that sometimes the problem does not give you the bounds in algebraic form, and you'll need to come up with the bounds. So here we have a square with vertices 0, 0, 1, 1, 2, 0, and 1, minus 1. Let's draw these points and come up with the bounds. So our points look like this. These are our 4 points, 0, 0, 1, 1, etc. And you can see that it forms this diamond, and a diamond is just a sideways square. Now it tells us that these are the substitutions to use in this case. One can come up with these substitutions by looking at the bounds and finding the constants, and that's similar to the previous problem. For now, though, we'll just go with what they tell us. Now, the key is to come up with algebraic forms for these bounds, so that then we can transform those algebraic forms for the bounds into algebraic forms for the bounds on u and v. So for example, this line here is the line y equals x. This line here, using y equals mx plus b, is -2 plus x. And this guy is 2 minus x, etc. But in order to do the substitutions, we need to solve for u and v in terms of x and y. So we are told that x is u plus v, y is u minus v. So we can do elimination and solve for u. So from here, u is x plus y over 2. And similarly, we can do elimination and solve for v. V is 1/2 x minus y. And now we can substitute in these bounds. So u is 1/2 times x plus y. So if y is 2 minus x, in other words, along this edge, then we replace y with that 2 minus x, and then that's 1/2 times 2 is 1. So in other words, this edge here becomes u equals 1. Similarly, this edge here, y is minus x, becomes u equals 0. And that means that u varies between 0 and 1. And one can do similar reasoning and see that v varies between 0 and 1 as well. So that means that this integral will have u and v bounds of 0 to 1, du dv, and x is u plus v, y is u minus v. We'll need to do that substitution, get everything in terms of u and v, and we need to find that Jacobian. So that Jacobian is next, j of uv, that is the determinant of this matrix, which is the determinant of this matrix, which is -1, -1, or -2. And then the magnitude of that, the absolute value is absolute value of -2 is 2. Okay, so our desired integral is thus this, where u plus v, that was x, u minus v, that was y, we're doing our substitutions, and this 2 here, that is our magnitude of the Jacobian, and these are our new bounds that we found on the previous slide. So this is nice square bounds now, it's over a unit square. And let me just say that geometrically, this 2, what is that geometrically? Well, this square has area 1. This initial square has area 2, because this side length here is the square root of 1 squared plus 1 squared is root 2. Root 2 squared is 2. So we're going from a base of area 2 to a base of area 1, as far as the area over which we're taking the double integral. And because we're shrinking down by a factor of 2 on each base of a rectangular solid, then we need to compensate by multiplying by 2 in the integrand. And that compensation is exactly what that Jacobian does. Okay, and by the way, this integral evaluates to 0. I've skipped the steps there. It's just a matter of boiling this out. We have u squared minus v squared. We know how to integrate u squared. We know how to integrate v squared. So it's just a matter of calc 1 a couple of times, and one can get the answer. Let's do one final example. I'm particularly fond of this one. We are given this ellipse, and integrating over an ellipse is bad. However, we can squish that ellipse into a circle with an appropriate coordinate substitution. And this problem, it just says in the ellipse, we're going to make that in quadrant 1, just to make it so that the answer is non-trivial. So the picture for what this does, we're taking this ellipse piece. We can divide both sides by 36. This is x squared over 2 squared. So the x part goes out to 2. Similarly, the y part goes out to 3, and we're in quadrant 1. So we're integrating over this piece initially. That's a piece of an ellipse. And we do this coordinate transformation, and that will end up making it into what? Well, we do that substitution. Let's find out. So step 1, we're finding the new bounds. We have 9 times 2u squared plus 4 times 3v squared is 36. That's the same as 36u squared plus 36v squared is 36. So u squared plus v squared is 1. So we wind up with the unit circle in quadrant 1. And integrating over the unit circle is much more pleasant because we can use polar coordinates here. In particular, this means that r would be between 0 and 1, and theta would be between 0 and pi over 2, going from 0 to pi over 2. And you can see that that would give us very pleasant bounds, much more pleasant bounds than trying to deal with an ellipse. So now it's just a matter of computing the Jacobian, and we'll be good to go. So we compute that Jacobian. Del x del u is 2, del x del v is 0, del y del u is 0, del y del v is 3. So we have 6. Okay, and what this 6 geometrically corresponds to is the factor when we shrink the area down. So this guy has 6 times more area than the new base over here. So we need to multiply the integrand by 6 to compensate. That's what the Jacobian does. Okay, so now we have our new bounds in polar, and that's how we want to integrate this. So our desired integral is the integral over the unit circle in quadrant 1 of, okay, x is 2u and y is 3b. That's our x times y from over here. And our Jacobian is 6. Yeah, so this is our x, y times the magnitude of j, uv. Okay, du, bv. Okay, but we don't want to integrate this in uv coordinates. It's this after all. So we want to change to polar. And in polar, r goes from 0 to 1, theta goes from 0 to pi over 2. Here we have a 36 times, okay, u is r cosine theta. V is r sine theta. That's our u. That's our v after changing to polar. And don't forget that when we change to polar, we need to include that r. And then dr d theta. So finally, that is a nice integral that we can evaluate with nice rectangular bounds. And again, that r that we stuck there, that's for polar. Remember how we always need to put the r there. And in fact, that r is the Jacobian of the coordinate transformation to polar, as we derived at the beginning of this lecture. So we wound up with this integral. And for sine theta, cosine theta, integrating that, use that sine of 2 theta is 1/2 is 2 sine theta cosine theta. That's the double angle identity. Whenever you see a sine times a cosine by itself, and you want to integrate it, same as 1/2 times sine of 2 theta. So this integral is the same as the integral of 18r cubed sine 2 theta, because that guy is 1/2 times sine of 2 theta, and 36 over 2 is 18. And this guy we can easily integrate. Integral of sine 2 theta d theta is negative 1/2 cosine 2 theta. So we can do that, and we end up getting 9/2. All right, that concludes chapter 16.7 on coordinate transformations. Have a great one.